talk because we have another speaker from Vienna, Dmitry Ponomarev, who talked to us about paleomagnetic imaging.
Something like this. Thank you very much for the introduction, Darren. And I'd like to say thanks to organizers in general of this great program. What I will speak about is sort of example of extension of some elements of complex analytic toolbox to 3 dimensions and in the form of harmonic function theory. So how it helps to solve a particular physical problem. And particular physical problem comes from paleomagnetic context. Well, should start by saying that this is a joint work with my collaborators in France and in US, and it is motivated by the following context. So paleomagnetic context is well, what is paleomagnetism? Paleomagnetism is anything which studies magnetic field of Earth and or maybe other planets if you have access to it. And it's usually done by geophysicists through studying the remanent magnetization of certain rocks. So they, roughly speaking, dig out the rocks in some craters, and they look for those rocks that contain some remanent magnetization. So those rocks were very rare to find, and they contain information about ambient magnetic field in which they were magnetized. So if such rocks such rocks are extraterrestrial, then studying their magnetization allows one to learn some information about the magnetic field on other planets. So this is the experimental setup for measuring magnetic field produced by such magnetic rocks. So here you can see the slice of the rock. So suppose we're lucky to find a good rock which was magnetized from ancient times. So it has some information of the magnetic field on Earth of that time. So we slice this rock, we glue it on the support there, and here above there is a magnetometer which goes which sees this rock through this sapphire window, and it's a scanning microscope. So it goes above it in a horizontal plane, and point by point it measures the magnetic field which it produces. Peculiarity of this setup is that it's only one component of magnetic field is measured. So schematically, the situation looks like this. So this is the sample magnetization distribution, and above it, at some distance h, is extremely small. The measurements are taken in a horizontal plane, and what is measured is a vertical component of magnetic field, E3. So mathematically, here's how it looks. So we have this magnetization distribution M. It has compact support. The sample is finite, and it produces magnetic field, and this magnetic field can be described by a scalar potential phi, and the relation between them is given in the form of this integral relation, and this integral equation follows from the solution of Poisson equation, which in turn follows from the simplification of Maxwell equation. So we have this interconnection between the magnetization and the magnetic field. And then what is measured, as I said, is only vertical component, so it's the vertical derivative, the potential. So here the red things are what is somehow accessible, even though only B3 is accessible in reality. And the blue is what we want to find. So magnetization is what we want to restore from the left-hand side. So this is inverse problem, and this is inverse problem with very bad prognosis. So actually, you cannot solve it because of there is non-unicity issue. So if you look back, magnetization enters this relation in the form of divergence. So that means that if you add to magnetization anything which is divergence free, neither potential nor magnetic field would notice this. So there is a strong non-uniqueness issue here. However, we still can say something. So if we are less ambitious and look at the magnetization of the sample on average, so just compute the zero moment, zeroth algebraic moment of the magnetization vector, which is three numbers essentially, to decide whether the sample how strong it is magnetized and what is the direction. Then this can be uniquely done from the data from B3 or phi. So this would be the goal for reconstruct this what is called net magnetization moment. So the average magnetization of the sample. So just finding three numbers essentially from all the measurements. And in order to achieve this goal, we developed two approaches. So one of them is based on the Kelvin transformation, and the other one is pretty much direct Fourier analysis, two-dimensional Fourier analysis. And in both cases, I assume that the measurements are measurements are always available in a limited area. So we measure above the sample of some the limited part of horizontal plane, and I assume that this measurement area is a disk of radius a. All right. So to motivate the Kelvin transformation, let's put ourselves in a hypothetical situation that we measure not on the plane, but somehow we have a measurement on a sphere encompassing the sample. Then the potential, and we somehow we measure the potential. It's not a realistic situation at all, but suppose we measure potential and on a sphere. So the previous formula can be rewritten in essentially in the polar coordinates like this. And then since we measure around the sample, outside of this sphere, everything is harmonic. So the Poisson equation is actually a Laplace equation. So phi is can be represented as expansion over spherical harmonics and in the exterior of the sphere. And important observation here is that if we take phi and we integrate it against first three spherical harmonics, so we take spherical harmonic with L equal 1 and J, there will be three of them with J equal -1, 1, and 0, and integrating against each of them by orthogonality selects here the term which is which will be 1 over r square, which has the factor 1 over r square, and integration on the sphere, so the measure on the sphere is proportional to r square. So what we have is that actually it doesn't matter on the over which sphere we integrate this, because the factor with the radius cancels out. So instead of we have data on the sphere of radius r0, so we can form such integrals. Here I write integrals in the form of the scalar product, and that's just the components of the vector, just to compactify notation. But because nothing depends on the radius of the sphere, it will be the same as the integral over very, very large sphere. And very, very large sphere is very beneficial to take, because then if we look at these expressions, when r is large, then for example, in denominator, r square wins over all other terms. So there is a great simplification. In numerator, also this colored term win, and that they are actually each of them is correspond to spherical harmonic as well. So eventually, the such integral reduces to the something which is just integral of m1 over the support of m, or m2 or m3, depending on which exactly spherical harmonic you pick. So what we get is that in this expansion, those first three coefficients are proportional to those magnetization moment that we are looking for. So that's that is to say that if we were in a spherical setting, we would just take the data and integrate it against the first three spherical harmonics, and then we would get those three magic numbers that we are looking for. So the situation will be extremely simple. And however, we are not in the spherical setting. We have data on the plane. We have limited data, and we don't have access to the potential. We measure only one component of magnetic field, which is the vertical derivative of the potential. So to remedy the first problem, it's natural to try to map things from horizontal plane where we have the measurements to the sphere. So and this is exactly what Kelvin transform will be serving us. So Kelvin transform can be introduced as a generalization of Möbius transform. So Möbius transform is built on the reflection essentially on the inversion. So this is the classical Möbius transform that maps between the half plane and the disk. So we need something some analog of it, and the analog will be built from the reflection, which is like this. So it's a reflection with respect to the unit sphere. So this corresponds in into dimensional setup to this to the this reflection. Well, if we do this, what happens is that we lose harmonicity, and well, that's so it's conformal map, but we lose harmonicity. It's not very good. So and this situation can be also fixed if we see how exactly harmonicity is lost by looking at this how this reflection acts on the Poisson kernel for the unit ball. So Poisson kernel for the unit ball generates all the functions harmonic inside. So by looking how this reflection acts on it, we see that we're missing some factor, and by adding this factor, we restore harmonicity. So Kelvin transform is in this case is this reflection, so change of coordinate, and then multiplication by the factor, extra factor. And by the way, here I give a good reference to the book of harmonic functions here, which I think is have this very nice written form. So that was a very particular Kelvin transform which maps between interior and exterior of the sphere that I showed on the previous slide. We need something something more different. We need to map horizontal plane onto the sphere, and this can be done by slight modification. So it's essentially we will be reflecting the data with respect to some auxiliary sphere, and such auxiliary sphere will have this position of the center and this radius. So they are carefully chosen in such a way that the functions harmonic in the upper half space, well above h, would be mapped into something harmonic inside the ball of radius r0. So that dictates essentially the choice of the position and the radius of auxiliary sphere with respect to which it is a reflection. Well, it has Kelvin transform has some nice properties. It's essentially its own inverse. It's isometry. It doesn't do much with respect to the angular variables in horizontal sections. But if we look how it acts on the normal derivative, so this is the normal derivative of the plane, something we will need, then normal derivatives goes to the normal derivative of the transformed function, and there is also a term which is a function. So this is very different from 2D. In 2D, normal derivatives by Möbius transform would be mapped to normal derivatives. So there is a slight difference to pay attention to. So, well, I just apply this Kelvin transform to our potential. We have very messy expression, and actually, if we try to integrate this against first three spherical harmonics, we won't get anything proportional to the components of net magnetization that we want to recover. So it's just because the angular dependence is much more complicated here. However, we introduced Kelvin transform in such a way that we mapped on a sphere which had a radius r0. So it was r0 is still some parameter to play. And if we take this r0 to be large, then the integrals against those two spherical harmonics will be proportional to tangential moment of net magnetization. So, well, this is not completely unexpected because we map something on the sphere of very, very large radius. So it's like we warp the plane, but we warp it not too much. So some properties, some of these desired properties that we had for the units for the spherical setup will survive. Well, normal third component doesn't survive this. So in particular, so this proportionality would be made more precise. So M1, M2 will be given in the form of this limiting integral, and that was if we had the data for the potential, but we can lift it up to the realistic data for the field, which is the derivative of the potential, because the connection formula that I showed you before, the radial derivatives are very easy to compute because everything can be expanded into the spherical harmonic. So eventually we end up with a formula like this for M1 and M2. So we know what we need to integrate and take the parameter R0 large. What to do with the last one, with M3? Well, here it's time to look at the asymptotics of this relation, the original relation. If we consider absolute value of x large, what we see actually is that M3 is the dominant term of this integral at infinity. So if we actually have the measurements over the entire plane, then we wouldn't need to do much. We would just take what we measure at infinity somehow, maybe integrate along a circle or to uniformize somehow, and then we would read it off from there. But at infinity is exactly where we don't have measurements. So we measure over limited areas. But still, this is important to keep in mind. And what serves the goal to recover M3 is the observation that the divergence of magnetic field is 0, and applying Gauss theorem and closing the cap over the putting a cap over horizontal plane, closing it at infinity where everything decays. We obtain that actually the integral of B3 should be 0, because B3 is a normal component to the plane. So integral of B3 has to be 0, and if we split further this integral in the plane into two parts where we have measurements and its complement, then the part which is complement, we can use the asymptotic expansion that I showed on the previous slide, and it has M3 as a dominant term. So, it should balance what we measure. So, and just by elementary rearranging the term, we get that M3 is proportional to the integration of B3 over the disks. So. And well, we can use the same idea to improve the previous formulas to bring it to the realistic case when we don't have measurements, when we cannot compute those integrals over the entire plane, but we have to be more physical, so is to deal with limited measurement area. So we split the integration range into what we measure. There we pass to the limit, R0 goes to infinity, and in the second term, in the complement, we take the asymptotic expansion, and before passing to the limit, we compute those integrals of the asymptotic expansion terms. And we well, what we get is the explicit formulas for M1, M2 in terms of the B3. So of course, these formulas have asymptotic character. So as they get better as the size of the measurement area gets bigger. So size of the measurement area is related to the radius a. So now we can look at a problem in a different way. So let's just, without mapping anything to the sphere, take Fourier transform in both x1, x2, and we can rewrite the integral formula that was before in the form of sum of the derivatives of the Poisson kernel for the derivatives of such function for which Fourier transform can be easily computed, and this Fourier transform is extremely simple. It's just this exponential, and because it's convolution and magnetization is compact support, then everything is essentially multiplication. Multiplication by k1, k2, which correspond to derivatives with respect to x1, x2, and well, x3 is essentially h before we substitute it, so it brings in this quantity, and we still have to integrate in the vertical direction because we operate with Fourier transform only in the horizontal plane. So that's a very nice formula, and important observation here is that actually what we are searching for is magnetization, Fourier transform of magnetization evaluated at 0, because that's the integral of the magnetization. So we need we want to extract it from here by expansion near the origin. When k is small, then those m1, m2, and 3 would produce something what we are searching for. And these expansions are justified because everything is very smooth. Fourier transforms of magnetizations are entire function. This is totally justified. The only trouble with this is that actually on the left-hand side, in order to compute Fourier transform, we need to know it everywhere in the plane, but we measure again only in the finite area. But we can do again this trick that we used before, split into the part where we measure and a complementary part where we can use asymptotics. And in the asymptotical region, it's if we go to higher order terms, there will be more and more quantities related to the magnetization entering the story. They are unknown, and here we can also expand to the higher powers in k, and in particular looking, for example, taking k2 equals 0 and looking at difference in the neighborhoods of different size of the origin of k1 equal 0. So we can generate the equations which would also produce us the explicit formula for m1 in terms of the integral of b3, and well, similarly, of course, you can do it for m2 operating with k2 terms. But you can actually improve those formulas, because if you look at neighborhood of the origin of the size k cube, then you generate another relation which contains this term, which is a little bit like magnetic garbage. So it's first order algebraic moment of magnetization, but it is the same term as enters as the previous relation. So we can combine them, and actually we get better by eliminating this term. We can get better estimate for m1. So before it was of order first order 1 over a, but now we know that if we integrate our field against this function, we get something which is of second order. Well, I think I don't have much time to talk about M3, but essentially you can do the same by operating with this term. So you take the real part, and then you do the expansion in the powers of absolute value of k. Then you can do you can try to improve things by approaching origin from some sectors and expanding things there and matching terms and generating more relationship. And you hope to eliminate other magnetic garbage term to get what we want with higher accuracy. And I just finish by showing how things work numerically. So numerically, we want so these are the formulas that I show first and second order, in particular for aiming at recovery m1. And so the true value is this constant horizontal line, and well, the second order estimate, the best one that I just showed you in the previous slide, is the approaches this curve as a goes to as a grows large much faster than the first order. And of course, you can hope to get something even of higher order. And similarly for M2, for M3, and if you try to see how robust it is with respect to the noise, adding 10% noise, it also survives this. And for M1, M2, for M3, it's not very stable. So you have to sort of do the averaging over some windows. And but yeah, so after this correction of the data, pre-processing, you can get something which is good. And so yeah, just to sum up, I tried to show the two different views on the two different methods aiming to recover the net magnetization moment, and one of them is based on a Kelvin transformation, which is a nice generalization of Möbius transform in classical complex analysis. And second is see how it matches with direct Fourier analysis. And in both of them, the important idea is that was not evident is to complement the measurements with something which is a priori unknown, but it's related to what we are looking for. So instead of just putting zeros there, as is usually done in most engineering contexts, so actually include what we are looking for in the asymptotics and then try to solve for it. And I think these ideas can be extended to other problems. So thank you for your attention.
Thank you very much. Maybe one quick question? Yeah.
Is there a relation between this problem and the vector Calderon problem?
Well, in Calderon problem, you want to reconstruct conductivity from the Dirichlet to Neumann map, right? And I'm not sure what is a vector Calderon problem. So you want to... yes, so...
in this problem, under the hood, there's also some elliptic problem in the domain, right?
Well, yes, it is. It comes from the Poisson equation, but in this case, it's the problem is in the free space, and it's inverse source problem. So it's just the source that is unknown. So so it is quite natural to write the integral for the integral formulation explicitly, and then try to.
One quick question.
Yeah.
So essentially, this is like a remaneWe level in several dimensions, but some of my colleagues would talk about downward continuation, probably when they're doing the Odyssey from the satellite. In your case, you've got the H minus X, which is very small. Can you do better by changing that during your experiment?
Well, experimentally, it's difficult. Of course, that would help a lot. Well, you cannot even turn this. It would be also helpful to measure at the other side of the sample, but this is also not so simple, because it's actually the sample is glued, and everything is very sensitive. So it's essentially it's very rigid setup. So it's, yeah, of course this would help, but experimentalists are reluctant to.
Okay, let's thank Bruce one more time.